continue our gradient descent convergence analysis for some very important next step, which is Lipschitz smoothness. But before that, I'm going to do a little recap. So we have done gradient descent analysis for Lipschitz continuity and convexity. Okay, and that was also given as a homework problem to see how we can extend that kind of analysis to Lipschitz smoothness and convexity. Okay, that was the homework. We'll talk about that. And as an example, derivation of Lipschitz constant for logistic regression. We have already shown that logistic regression loss is strongly convex, but is Lipschitz smooth, not strongly convex, Lipschitz smooth. But what is this Lipschitz smoothness constant? Um, and then we'll then move on to strong convexity and so on. So that will follow. Um, Also, the Colab notebook I shared last time has all of these elements, all these different algorithms implemented for the spam detection. Right, we'll keep running through that. Um, okay, so again a recap. The idea behind gradient descent is you want a direction and you want a step size. The direction is denoted as delta, or in this case the direction happens to be the gradient direction. Negative of the gradient direction, and the step size happens to be negative, or rather gamma, negative gradient and gamma. So how do you get an epsilon approximate solution is a question. As I said, the analysis would depend on the nature of the function as well. What we saw is Lipschitz continuous and convex functions, where we get one kind of convergence, we're not very happy about it. So let's recap why we are not happy about it. I've also slightly changed the indices just to be consistent. I've made all indices into t equals 0 to t minus 1. Okay, so we are going to start always with x0. Okay, x0 was here, suppose. So this is our x0. So we'll go from x0 to x1 and so on. Or t equals 0 to t equals capital T minus small t equals capital T minus 1. So for this analysis, recap that initially it was simple algebraic manipulation where we wrote the dot product in terms of squares or differences and difference of squares and so on. And the fact that even the tth iteration doesn't seem to have reached x star, that inequality basically lets us get rid of some of these terms. For example, this term we get rid of. And we also do telescopic summing. So our first trick. Again, I'm recapping these tricks because we'll have to reuse these tricks now when we come to other convergence proofs. This telescopic summing. So hopefully we'll see all tricks under one hood. What was the second trick we had? I mean, actually, yeah, maybe the first trick was trick one was basically a dot product as sum of squares, or as difference of squares. Okay. So this was one trick. The second trick was telescopic summing. What were the other tricks? A third trick was this one, the extreme right expression here. Yeah, fortunately now because we are having index t equals 0, t minus 1, the inequalities become simplified here. So okay, so note that simplification of notation into lower index becoming t equals 0. Otherwise, we had one more inequality last time. We tried to avoid that complexity of additional inequality. So that has been saving for us. Okay, and finally, we'll see how this in the last class gave us the final convergence. Now there we talked about order and rate of convergence as well. We talked about P convergence and Q convergence. So this is our trick 3. Just let me just put this on writing. So trick 3. This was minimizing RHS as a function of some parameter. This was eta, that the when the LHS in the inequality which is less than or equal to RHS, right, does not have that parameter. That was a basic idea. That's a trick 3. Okay, so overall then we could go ahead and then show that the left hand side, which had xt minus x star, now you can replace each of these t's with x hat, which is the argument over I of f of xi. You can replace it with f of xi basically. This left hand side, if you bring in f of xi everywhere, sorry, f of x hat everywhere here, then you'll basically get a summation over all of these, the same term basically. So this is less than or equal to, or this right hand side is greater than or equal to t upon t of f of x hat. So that you're summing this up t times minus f of x star. Okay, so this because I started index with 0, this cancellation becomes easy. Otherwise, there'll be a little bit more work you need to do. Okay, so this is the final result we had got. To get f of x hat minus f of x star less than or equal to epsilon, you needed r square b square by epsilon square iterations. So it's growing quadratically in the reciprocal of the error margin you want. Right, but can it be a slower growth is the question. Right, so and we specifically again give you this example. It goes to 0 as t gets large, independent of the dimensionality of x. Those are advantages, but to get an error of 0.01, we require 10 raised to 4 r square b square iterations, where b is a Lipschitz continuity constant and r is the radius that contains the initial iterate. Okay, so I will not go into that again, though it's something that we will have to use time and again. So that is a requirement. We'll often require that the starting iterate is within the radius r. Okay, so let me just draw that for completeness sake. So this is our image, and I had specifically pointed out that this r is characterizing the initial iterate distance only. Okay, so question we had left ourselves with is, can this the number of iterations grow more than the quadratic square, or rather squared function, squared function of the reciprocal. The margin, which you want to be as small as possible. So smaller the margin, the more the time it will take, obviously, but then we don't want it to grow so fast. Okay, that is our desire. Okay, so towards that I said, can Lipschitz smoothness bail us out? We know that Lipschitz smoothness is not necessarily a generalization of Lipschitz continuity. But um, for bounded functions, no, for well-behaved functions, yes, Lipschitz smoothness does imply Lipschitz continuity. So it's more general in the practical scenario. Right? So though not always more general, and Lipschitz continuity. We saw how smoothness is more in practical settings more general. And what is it doing? It's saying I'll put an upper bound on the rate of change of the function. Okay, this L characterizes that upper bound. Um, okay, so now how does this help? This was left as a homework. And before we went there, I had left you another homework also. Okay, so if f1, f2 are smooth convex functions with parameters L1 to Lm, then we know that the convex function is smooth with parameters summation y, li, etc. Now, can we do something and something more, let's say, with respect to spectral norms, etc., to derive a bound on the value of L for the gradient of f, where f is the logistic function loss. Basically, what we're looking for is the Lipschitz smoothness constant. Okay, so we call this as the first order condition for Lipschitz smoothness. So we want to determine this L. Anyone had any success? This was a homework problem. Any success on this? So first thing I would like you to recall is that we have already talked about Lipschitz smoothness, okay, of the logistic laws. So let me recall. Okay, so recall. But the only thing is we didn't determine L, right? Smoothness L of the logistic laws. So how did we derive that? Anyone wants to recall? What was the proof methodology?
By using composition of functions.
By using composition of functions. So I'm just going to put that as it is from our previous derivation. You use composition. And we saw that for the simple function f1, right? f1t, which is log of 1 plus e raised to t, which is the basic element of the logistic laws. L could have been half or 1/4, whatever, right? Basically anything that upper bounds e raised to t divided by 1 plus et squared, e raised to t whole squared. And then we showed that you can have f2 is yi minus yi theta transpose xi, right? And yeah, you can basically show that you can the composition is rule is going to work out. But let's get more specific. Okay, so this f1, f2 theta is all fine, but let's get more specific. So now how do I get the Lipschitz constant? Let me. So that we proved. Any thoughts on how to get the Lipschitz constant? I gave a hint here. There was a matrix involved. Yeah, somebody has some idea. Somebody unmuted herself or himself. So this idea, right? We could talk about this norm, spectral norm. How did the spectral norm help? What was the notion of a spectral norm? Or how are these vector induced matrix norms derived? There was something like, no, if I have a vector, yeah,
Supremum of overall x bar v vectors, norm of av upon norm v.
yeah. Okay, and what was the spectral norm?
Uh, when you have the two norm, uh, then the spectral norm was the largest singular value of a.
Okay, the largest singular value. Okay, good. Um, so this turned out to be lambda max, largest singular value. But what's the connection we have with that? As I said, two norm is critical here. But let's try and complete this proof. Complete the derivation, right? So the previous slide we have got the L when you have F1, but what is, let's write down more specifically what the logistic loss is. What is the logistic loss? Yes, anyone?
Log 1 summation I 1 to n log 1 plus e raised to minus yi theta transpose xi.
Right, right. So I'm having a problem writing, getting my pen to write. Okay, so basically the simplest aspect is that you have internally this let's just call it F, I think we call it F1, right? F1. So my logistic loss looks like, is it like F2 F1 T, and what is the form of F2 in terms of what you just said? We can ignore the summation.
Log
Okay,
log 1 plus x
no, that is there, that is F1 is already there, log of 1 plus e raised to t. I'm talking about F2. Should F2 be inside or outside?
inside, right? F1 of x.
Exactly. So F1, and what is I think I'm, yeah, what is the form of F2t? Actually it should not be F2t. What is F2? The function of
Theta.
theta. But what is the form of F2?
Fine. Minus yi theta transpose x.
So can I just write it more generally? I mean, I could even write it as a matrix multiplication, right? If I have lots of um, features and examples. So this for a single example, of course, it's a vector. So let's just write down, right? I'm just going to write it as exactly as I did in the previous slide, right? Y theta xi. Oh God, this was my I is yi theta I transpose. Sorry, theta transpose xi. But I'm going to write it more generally as just theta transpose p, some p. Okay, and now I told that composition of Lipschitz continuous is Lipschitz continuous. I in fact proved it. But what is the Lipschitz constant is the query, right? How would you get that? Can we make use of some property like this? Something like matrix norm. You need matrix norm or vector norm is good enough? So let's write down the actual gradient, right? So what's the gradient of F1, F2, theta? What is the gradient looking like? Will we have, say, F1, the derivative, times F2, theta, into, so this P trans, okay, so this P transpose, P has all of PI if you want, PI transpose. And if I substitute for F1 dash, what is F1 dash? We had to form the expression for F1 dash, right? Et 1 upon Et upon 1 plus e raised to t. What would that turn out to be? What you have to realize is F2 applied to theta will give you an x, right? And then that pi. That when you multiply by pi transpose, pi transpose, what will that give you? A matrix times a vector. So I think just to simplify the whole thing, you'll have some scalar sitting out. Okay, f1 dash will have a scalar, but the whole idea is this will be proportional. Okay, so get the form of the expression theta transpose. I think you'll have theta transpose pi transpose, something like this. This is a matrix. This is the matrix I'm referring to as AI. A, call it AI if you want. This is the A, I, theta transpose AI. Right, and then now when you start looking at the difference of two gradients, or even the Hessian, if you want to upper bound the Hessian using an Li, that L will really depend on something to do with the pi transpose. In fact, something to do with the spectral norm of pi transpose. Okay, so I'm not going to derive this, but roughly what's the set of these PIs is going to have an influence on the L. Okay, so L, we already saw that for F dash, the estimate of L we have is like half or 1/4, right? So you'd probably get, okay, so this, let's call it L for logistic regression. Okay, I'm not going to ask this in midsem. This is not really a midsem question. So, but maybe for simpler functions, you should be able to derive. May not be for logistic regression. But the L of logistic regression should approximately be whatever your half or 1/4. Since we want an upper bound, a tighter bound is better. So 1/4, let me take it. 1/4 from the previous slide times that comes from the theta transpose times, you would expect a lambda max of the pi transpose to come up. Okay, so this is to give you an idea that okay, this is proportional again. I mean, I've really dropped other factors, but the key here is that I have gotten an expression in terms of this lambda max. Okay, so this is this, by the way, this comes from Cauchy-Schwarz inequality. Okay, so this I know is less than equal to, say, the norm of. Okay, so I didn't complete it. This was assuming that you had worked out. So you'll have some, some constant. Okay, in fact, let me just put this as the logistic regression LLR is, say, eta. Let me call it eta. So you'll have some eta times norm theta into the norm of pi transpose theta. Okay, so this is Cauchy-Schwarz. Okay, the key is to see where the eigenvalues start surfacing. Okay. Unless you have some specific question, I'm not going to go into more details. This is the sketch. This is how you derive the Lipschitz constant. Okay, let's move on to the other more important homework. Did anyone give some thought to it? How do you derive this analysis for gradient descent with smooth functions? Anyone? Okay, so let me provide some leads here. As usual, we'll have to think of what's the next expression or next inequality to apply, right? So if you have smoothness, you could start with this f5 less than equal to fx plus the dot product between the gradient at x and y minus x plus L by 2 norm y minus x square. So what would be a substitution for y and x? So naturally you would pick y to be xt plus 1 and x to be xt. Right, and as usual we know that we are doing gradient descent, so let's just give it a name gt. This y minus x is gt. Well, it's not just gt, it's also gamma, right? So it's gamma gt, step size. Likewise, this y minus x norm square would be gamma square norm gt square. What's the next step? Okay, so this I have just shown. Oh, by the way, I made a mistake here. There should be a negative sign. Okay, we are doing gradient descent. This will have a negative sign, minus gamma gt. Now I have come to the next inequality where I've just substituted. Nothing smart has happened. Again, I need your help. What do I do here? Can I apply trick 1, trick 2, or trick 3? I have a recipe. Please help me choose from that recipe which trick to apply next. Okay, so this is really a training. You have to suggest trick 1, which was algebraic manipulation. Trick 2, right? Algebraic manipulation means the expand in terms of squares, right? Which is already there. So it doesn't look like it'll be applicable. Trick 2 was telescopic summing. Should we get to telescopic summing so early on? And trick 3 is observe what's on the left hand side, what's on the right hand side, right? Minimize upper bound with respect to parameters that do not characterize LHS. So do you have a case like that here? Anyone?
Third.
Okay, the third one comes to your mind. I mean, there could be more tricks we add to our kitty, but from these, looks like third is the most reasonable one to apply next. Okay, so let's do that. And now to apply the third one, what do I have to do? I will
Bound with respect to gamma.
Yeah, I'll minimize the right hand side by differentiating with respect to gamma, right? So set the DRHS by d gamma to 0. What you get by that? First term is independent of gamma. The second one will be just -1 minus 1. Okay, so norm GT square will remain everywhere. Okay, so if you want put a norm GT square minus 1 plus, very simple, L times gamma, norm GT square is 0. I know that we have not yet arrived at a critical point, so norm GT square is not 0. Therefore, minus 1 plus L gamma is 0, which means L equals 1 by gamma, or gamma equals 1 by L rather. Okay, so this applies, this convergence holds in the worst case. I mean this value gamma holds also in the worst case. So yeah, there's no need for me to keep repeating this. We have already seen its use. Let's see if this gives us something useful. Cases with minimizing the upper bound and maximizing lower bounds. That's the other aspect, are frequently used tricks. So we have here resorted to minimizing upper bound. Okay, so we have already seen that the value here is gamma equals 1 by L. Let's substitute. Now this is interesting. F of xt plus 1 is less than equal to f of xt minus 1 by 2. Oh, sorry, 1 by 2L GT norm square. Okay, so we are saying that the there's at least so much minimization possible in every step. Look at this, very interesting. We have not even used convexity, huh? So with just smoothness, you should get excited by this fact that the gradient descent rate is giving you some kind of guaranteed decrease. Okay, let me highlight this point here. So even without convexity, this is even without convexity. Let me make even without. So assumption L smoothness gives some guaranteed decrease in every iteration, right? So this should be very exciting. Right? So this, yeah, again, I'm adding this note here without even convexity assumption. Okay, but now if you bring in convexity assumption, maybe we can show something more. Okay. So what would be the next step? Well, we haven't used convexity. I mean, almost overemphasizing that part. That's what we'll do next, right? Okay, so I'm just recapping minimizing upper bounds and maximizing lower bounds, how these tricks are useful. Here, for example, we got gamma equals 1 by L. But let's just contrast for a minute what happened when there's a worst case, basically, worst case, okay? The best case could have been different. So this is the worst case in the case of Lipschitz smoothness. In the case of Lipschitz continuity, okay, this is a loose smoothness. But let's contrast this with Lipschitz continuity. The worst case we got was gamma equals R by B into square root T. So just to contrast. But again, this is not the only value. This is a worst case value. Or tightest case, these are values of gamma yielding the tightest upper bound. Upper bound, yeah. Okay, so you could always have better values here. Any questions? Okay, so now let's go on to the next part. Um, so you can flip it differently. You can say, oh, I know that fxt plus blah is 1 is less than equal to fxt whatever, right? Now I can say this can also be used to get an upper bound on the gt square, norm gt square. What's the next trip I would apply? I should apply. Should I apply convexity or telescopic summing? The two tricks left in my bag, right? So convexity is not a trick. I mean, which trick slash assumption? So let me not convexity assumption, telescopic summing. What is tempting, right? At this point, if you do telescopic summing, what will happen? Would we have some cancellations? You can also go for some squared expansion, but nothing seems to work here, right? Any voting? How many would go? Anyone would go for convexity? Anyone would go for telescopic summing?
Convexity.
Convexity, okay. Dai, thanks for spelling that out as a possible assumption.
Telescopic.
Okay, there's another opinion as well. Nice to hear that. Yeah, you are good to see that all of you thinking. You can try both ways. I'm going to go by telescopic summing because I'm just finding it a lot intuitive here that the fxt plus 1 can get cancelled with fxt, the next iterate, or rather fxt can get cancelled with fxt plus 1 from the previous iterate. Okay, so what I can do is like summation. First I'll bring, let's say I have to get these fxt plus 1 and fxt on the same side just for ease of operations. So 1 by 2l norm gt square is less than equal to, now I just want to leave some space here, fxt. I know the iterates are decreasing every step, so I can take f of xt minus f of xt plus 1. I put a summation on both sides. I'll always start with t equals 0 to capital T minus 1, just to be consistent. See what happens. Okay, so this is the trick I've gone for, telescopic summing. Okay, so let's see what happens when you do this. Oh, there's a small mistake here. T equals 0. Yeah, summing above inequality for t equals 0 to t capital T minus 1. So as expected, everything gets cancelled out. So you'll have f of x0 minus f of x1 plus f of x1 minus f of x2. That's exactly the reason we invoked telescopic summing. So I would like to strike off everything. All of these get struck off. Okay, except for these two last terms, which survive here, right? F of x0 minus f of xt. Okay, so these surviving terms, on these, could I apply the next pending trick? Do you think now the time is ripe to apply convexity? Okay, or is there some more trick we should apply? It's not a trick, by the way. Again, convexity is an assumption. So far, we didn't make that assumption. So that's important to note where we make that assumption. So without convexity, we can go so far. We can say there's sufficient decrease, and this is all, without convexity. We are saying that the there's a sufficient decrease. F of xt is x0 minus f of xt is at least the sum of all the gradient squares, right? So we have made sufficient decrease using Lipschitz continuity. I've already got sufficient decrease from 0th to tth iteration using Lipschitz smoothness. Okay, so yeah, this is not bad, but we're just greedy and getting and trying to see, well, can we do even better? Let's do that. Now, if you have to apply convexity, I don't want to again, the derivations I'm going to make more and more crisp, because we want to build on what we derived in the last class, right? So in the last class, you might recall that we had this analysis too for Lipschitz continuity and convex function. So in fact, in the last analysis, we began with with convexity, and then brought in Lipschitz continuity. So here we did the other way. My previous analysis, we first brought in convexity, and then we basically saw that norm of gradient sitting there, and then use Lipschitz continuity. We already saw, so mostly convex functions are Lipschitz continuous, right? I mean, we go back to our derivation earlier. So most, again, I'll keep this very loose here. I will not keep on invoking results. So let's invoke the convexity of F. Now, how would you use convexity? Again, if you remember the analysis, we'll probably take x0 and xt and gt, but you have to now remember, somehow we have to get an x star, right? We want to know how far we are from x star. So far we have not got to x star. Okay, so should we apply the convexity at x0 and the convexity as at xt with respect to x star? Okay, how you apply convexity is what I'm talking about. Fine, we want to apply convexity, but how? Okay. Anyone wants to suggest how you would apply convexity? Right, such that x star, the optimal, which from where I want to measure the gap, right, also starts appearing. Any suggestions?
In the last analysis, we invoked a convexity on f of xt minus of x star, and that expression had a norm gt square some units. So maybe we can go along that way.
Yes. So that's exactly what we'll do. So the analysis we'll actually get from previous. Okay, so I'm not going to again, derive everything all over again, just presenting the derivation. So I'll be using a lot of color coding here so that you can quickly register. So remember, we had this expression from the definition of gradient descent. And then what we did, we used this algebraic expansion. This is the trick 1. And then what we did was the expression on the left is in pink here. We expanded. That's exactly using the trick 1. Sum them over. So that's again telescopic summing we had done, right? So it's not that trick. A trick can be used only once. So trick 2 again. This is a second invocation. Possibly this entire proof, we are using this trick for the second time, which is fine. Okay, and then we said, okay, this left hand side is equal to some expression. Now this we had a way of dealing with this xt minus x star, we said this is greater than 0. That comes next. So this is greater than 0. And then the other part was using convexity. On this we use convexity. Okay, so all this is recap. Okay, everything is recap here. So we basically boil down this expression. Now this is where we had invoked Lipschitz continuity in the previous analysis. We are saying no, there's no need. We'll now go back to our analysis from Lipschitz, smoothness, and telescopic summing. Okay. So yeah, this combining 8 and 9. Okay, so combining 8 and 9, what do we get? What we had got was f of xt minus f of x star, which is exactly the form we want. This part being upper bounded, lower bounded by f of xt minus f of x star. So we just able to use that here, is less than equal to the terms on the right. Now I have deliberately put the some parts in blue. Okay, and you'll see why. Okay, so this expression, this should be all fine so far. Any questions? So now how would you use this? If you are fine with this expression, how would you use this in conjunction with Lipschitz smoothness? Should we just use the gamma value of 1 by L here? We have something in terms of gamma. Should we try and minimize this with respect to gamma, or just use gamma equals 1 by L?
What I meant was that we have a lower upper bound on GT mod GT square, maybe that.
Yeah, I mean you can bring the mod GT square to the left hand side and all, right? That's what you're saying.
Yes.
Yes, that is true. The summation we have an upper bound, but we still want to do something with gamma. Okay. So in the previous analysis, what we did was minimize this with respect to gamma, obtained right gamma. What I'll do here, without this is going to be a jump here. We'll assume that rather you can show that gamma equals 1 by L is good enough here also as an upper bound. Okay, it can be shown. We need to do something with the gamma here, that the gamma equals 1 by L is good enough here to here as well to maintain the upper bound. Okay, now why is it? Probably I'll not uh, spend that time in the class. So this is going to be a slight departure. Okay. So the RHS, we're going to set gamma equals 1 by L. This gives you slightly different expression than earlier, and this upper bound still holds. I mean, so the gamma we had got earlier, just as a hint, right? What was the gamma we had got earlier? It was RB upon square root T. Now it's possible that RB upon square root T is indeed, yielding a value which is less than 1 by L. That's how you'd prove it, right? And that's actually the way of proving. Okay. So if it holds for 1 upon L, it holds for anyone else. Basically, that's the idea. So there's no rocket science here. I mean, if you want, I can write that part. Right. So since we had found the lowest value, the RHS, or we have found the gamma yielding the lowest value of the RHS. So this is any other gamma. So what should be a problem, right? I hope you got the idea. That's the proof methodology. If any other gamma was found which or a gamma was found which minimizes the right hand side, why not gamma equals 1 by L? That also should work. So using that analysis or that argument, we'll continue our analysis. Okay. So I'm just copy pasting this argument here. So with that, yeah, gamma by 2 becomes 1 by 2L. 1 by 2 gamma becomes again L by 2. So hope this is all fine. I had put this in blue deliberately so that the right hand side, because now I'm going to find some other value for it using gamma, which is greater than the previously found lower bound. Okay, that should be fine. Okay. Okay, so then continuing, what do you do with this component? Okay, 1 by 2L. This is exactly what, sorry, I forgot the name, but whoever pointed this out, thanks. You had a lot of foresight, and that's exactly what we have done here. Let me use a slightly different color. So this we had got from 6. Okay, so I'll go back to 6. This is exactly where we departed into convexity. So 1 upon 2L sum of all the norm GT squares is less than or equal to f x0 minus f of xt. Exactly as pointed out by one of you. We are now just going to use this upper bound. This is therefore this this part. So 6. I just want to recap in case you're losing track. It's 1 upon 2L summation t equals 0 to t minus 1. Norm GT square is less than or equal to f of x0 minus f of xt. That's it. So I've just substituted for that f of x0 minus f of xt here. And we seem to be all set. Now next, what next? Again, let me ask you a question. Since you have led the discussion so far, I'm really appreciative of that. Can you help complete this? That'll be a real good success. How now I want some analysis. If I want f of x0 minus x star, or sorry, f of xt minus f of x star to be less than or equal to epsilon, how many steps should I take? How do I get there? A little bit more work is required to get there. Okay, I'm repeating my question. How to go from here to the convergence? Well, what we mean by convergence and kind of speed of convergence for upper bound function value, epsilon upper bound on function value. How many number of iterations? How do I get there? Any suggestions? Yeah, please speak up. You got so far. This should be possible. So do you see some terms cancelling or there's no cancellation? Is there some cancellation here?
We can take the terms in yellow to the left.
We can take the terms in yellow to the left. Okay, great. What else can we do? And then what will happen as a result?
The sum becomes from 1 to capital T.
Sum becomes from 1 to capital T. And what happens to f of x0? F of x0 vanishes.
It
That
gets
happens.
cancelled.
Yeah, so it gets cancelled. F of x0 will get cancelled. And what will happen? What else will happen? The capital T will remain, right? So it's simple. Okay, so the first thing we realize is that this guy will get cancelled out. Okay, so rewriting the math. Okay, so this is exactly what I was trying to show. This part, when you bring it to the left hand side, f of x0 gets cancelled out. And f of x star, what happens to that? You'll have to do Two additional summations? No, right? So there's a little bit of adjustment going on here. So just make a careful note. So we had f of x 0 minus f of x star. So there's f of x 0 minus f of x star, and then there was an f plus. So let me just use this, right? Minus f of x 0 plus f of x t. Right? This is what comes to the left hand side. Plus then you'll the regular term. So t equals 1 to t minus 1. So these are critical mistakes we can make and jump to conclusions. That's why I'm spending a little bit more time. So the f of x star should not be doubly appearing. I mean, it should have the right number of appearances of f of x star. And here, fortunately, what happens is some of these terms get cancelled. This terms gets cancelled, but the f of x star switches its affiliation to f of xt. So therefore, we get back where we began with, right? So which is the same index, same summation. Indices have changed. T equals now 1 to capital T of xt minus of x star. Okay. So very too often people make mistakes by jumping and not writing terms very carefully. So please be careful. So then now we are done. Are we done or something more? Can we use Lipschitz smoothness once more? Last step. And I'll tell you, this is really the last step. Could we do something with the radius? Could we do something with, you know, you remember the R, right? Expression we had that bounding the points. What should we do next? You know, this is slightly longer than the previous proof, but we are there almost.
The RHS is less than equal to what? LR square by 2. The RHS.
LR square by 2. Okay, let's write that down. Okay, and what else can we do? So this is fine. And what can we do about f of xt minus f of x star? What did Lipschitz smoothness guarantee?
Oh, the function value decreases its iteration.
Recall Lipschitz smoothness at the function value decreases at every now how by it decreases by some norm gradient square, right? Which we'll not get into again. I don't want gradient coming up here again. Function value decreases at every iteration. And what else? So that how does that help again?
So each f of xt is less than equal to f of x of capital T.
Right. So f of xt.
No, greater than equal to, sorry.
But what happens to f of xt minus f of x star? That's the question.
F of x star is anyways a constant. So
right.
f of xt is greater than equal to f of x of capital T. So even if you subtract both, the inequality holds. Then if we sum that, the RHS will become t times f of xt minus.
Okay. So can I say this is greater than equal to?
Yeah, t times f of xt minus f of xt.
Okay, so let me write this down here. So each of f of xt is greater than. Okay, let me write. Consistent. Okay. So this f of xt, capital T, we know is less than equal to f of xt, small t, for t equals 1 to capital T minus 1. So because of that, now I can just plug in f of x t consistently here. Okay, so I'll just say this is f of x, this f of x t. I'll replace with f of x capital T. Okay, of course, there's a outer bracket minus f of x star, which is as it is. Okay, so this part I have just replaced. Okay, so with that, we are actually done. Right. So what is this left hand side? It's the same thing being some capital T times. So how many times? We just be again mindful of the number of summations. T equals 1 to capital T. We started with 0, but that x0 got cancelled out, so we don't have T plus 1. We just have T. Okay, so then we seem to be set. Okay, so again, I've just written the same thing down, right? So it's the same argument that let's copy this part, right? It's just reason. Okay, so with that part, we are able to now replace f of xt with this part in pink, f of x capital T. I've now already divided by capital T here. That's I took one more jump, but it's the same idea. So this whole thing now on the right hand side becomes L by 2t x0 minus x star norm square. And you've already gone ahead of me and you said this is less than equal to L by 2 t r square, L r square by 2t. Okay, with the with the assumption we had from earlier, assumption, right, that all the points are, or rather the first point itself is within a radius r. Okay, so now with this, so again I'm just recapping. This is an additional assumption we have used here, r square, lr square by 2t. Now what is this? How good is this? I want function value reducing by at least epsilon. How many iterations will I take? Okay,
Omega 1 by epsilon.
okay, 1 by
Epsilon.
okay, let's do that. 1 by epsilon. One small notice, we can make this equality. By the way, it doesn't have to be equal. This was yeah, just make it equality. We can assume that this r is exactly x0 minus x star. Okay. So with that, yeah, let's try and write down the if you want this to be less than equal to epsilon, then what do we know? We need for this a sufficient condition sufficient that this term is less than equal to epsilon, right? And so what does this mean? Exactly as pointed out by one of you, the t should be at least r square L by 2 epsilon. So is greater than equal to. We rightly pointed out that this is related to the omega rate of convergence, omega, but we have actually resorted to p convergence. Okay, so which we have given us extra reading. Hopefully post midterm, if we find time, we'll go over it in some more detail. Otherwise, it's just extra reading until then. What is important is this this nature of inequality, right? The lower bound we have is r square L by 2 epsilon. Okay, so what does this translate to? So an error of 0.01, we need 50 r square L iterations. This is 2 epsilon. In the Lipschitz scale, it was 10,000. Okay, so we see it's a significant reduction. At least so many iterations we require. Significant reduction though. Okay, so this is the final result. given L smooth convex function, gradient step is step size gamma equals 1 by L. You achieve a solution xt such that f of xt minus f of x star is less than equal to epsilon and r square L by epsilon iteration. Again, my point is this step size, this holds, but it also holds with any other step size. It's like the worst case step size. Okay, recall that this gamma, recall this value was to give a lowest upper bound. Okay, so any other gamma will only help with that upper bound. Okay. In practice, however, the L is not found like this. I mean, L could be inspired, or the gamma could be inspired by the value of L. In practice, the back line search, line slash ray, we also call them ray search because the gamma value should be non-negative. Okay, so this is going to be part of midsum because it's important. The way we have developed on the previous proof to now show one more proof. What I'm going to do now, I mean, please stay on because you'll get a glimpse into how we can strengthen this further. And strengthening is really coming from this kind of analog or close cousin of smoothness, which is called so smoothness was this, right, which was giving us a quadratic upper bound. But now what we're going to have is a quadratic lower bound function in the form of the yeah, we'll have quadratic lower bound as well. The form of strong convexity. And how does strong convexity influence? Right, let's now get a glimpse because these are very related. I know I didn't give this as homework, but I'm going to help you understand this. We won't go too fast, but let's make some progress. Okay, so one important point I also want to bring up is the notion of we for Lipschitz continuity we had this matrix AI, right, which was xi transpose. So what quadratic upper bound, right, what was dealing with Lipschitz continuity was lambda max. Okay, so and that was early today, right? So we saw earlier today the connection of Lipschitz L constant, right, L factor for L continuity with the lambda max, right, the curvature associated, the max curvature or direction of max curvature associated, because you're trying to upper bound. Now I can give you an idea, I mean a hint that this when you start looking at quadratic lower bound, you'll be dealing not with the max but with min. Okay, because you're looking at the minimum curvature, you're looking at a minimum upper bound. Okay, so I mean also you all know that this is related to Hessian, right? The previous one was related, I mean also related to Hessian. Hessian square, right? Hessian greater than or equal to mu I is what the quadratic lower bound is talking about. Okay, and it turns out that this has association connection with lambda min. Okay, lambda min of that of the matrix we talked about earlier today. Okay, in general you can show, so these L by mu will start surfacing. So you'll basically have conditions like this. Okay, so this. So what you'll have in practice is something like mu, which will be less than equal to lambda min. So mu can be less than lambda min. It doesn't have to be lambda min. And lambda max, which will not be greater than L, will be less than equal to L. Okay. L will be further away. And the whole implication of this is, or the association of this is the ratio. So I mean the ratio basically of the largest and smallest eigenvalue is the condition number of a matrix. You must have heard terms like ill conditioned matrix. So this, if lambda max by if this happens, obviously lambda max by lambda min is less than equal to L by mu. So you want to see the L by mu factor coming up soon. Just to kind of mentally prepare you why this L by mu comes in. This lambda max by lambda min is the condition number of matrices. L by mu is a factor we'll see soon. Okay, so just so this associated with the condition number of the matrix. Actually, it's associated with the condition number of the Hessian matrix. So we didn't go that far, but a Hessian matrix of say logistic loss. Now, ill-conditioned matrices are basically when the lambda max by lambda min is very high. So with the small change in the matrix value, or numerical computations will completely change the iterates. That's when one implication of ill-conditioned matrices. So it basically is like saying, oh, the lower bound and upper bound curvatures associated are very far away. Right? That means there's too much oscillation. The closer these come together, the lower and upper bound curvatures, in some sense, the more well behaved, less ill conditioned the matrix is. Okay, so let me just associate this with so this point at the top. What we are trying to say is here, right? I mean, in general, this is not this particular point, right? What we are trying to say is the closer the lower and upper bound curves are, the better conditioning, or you can say, or behavior of the algorithm will be. We'll see more of that a little later. But just to give you an idea that strong and strict convexity, strong and convexity and smoothness, Lipschitz smoothness are very closely related. But this is a little bit of insight, but let's look at the algebra. Okay, so what's the analysis here like? What we have done right now is using convexity alone. So just using convexity. Let me make these notes. So what you have done here is using convexity alone, and I'll bring in strong convexity very soon. You see this expression, which we have been always manipulating with respect to sum of squares, right? This expression. So now I'm just going to bring that up. If you had strong convexity, you could do something more with this term. That's what we are trying to show. This is you only use convexity alone. So how will this change when we have strong convexity? Well, this GT transpose xt minus x star will be lower bounded, not just by f of xt minus x star, but also by mu by 2, this norm of xt minus x star square. Right? This is a stronger lower bound, and that's on the LHS here, this LHS part. Okay, so what we'll do is we'll basically put these two together. What are the terms you're putting together? On one hand, we have this f of xt minus f of x star. Okay, and then on the other hand, we have mu by 2 norm xt minus x star square. Okay, that remains. And then we have this term on the expansion. This is the analysis, previous analysis. This, as I said, this the trick one. So this entire expression you see is coming up here as it is. This expression basically gt minus is if we substitute for it here as an equality. So we get the same. Same inequality with some inequality with some equality substitution. We have got rearranged slightly. Okay, this is just rearranging terms. Okay, so from here I want to reuse different components of analysis that we have already done, like of convergence. Can we go from here to convergence rates for strong convexity and smoothness? Is the best? Is that the best convergence I can get? What are the best convergence I can get? The best convergence I can get largely is when you use both of these very strong conditions. Okay, so I'm going to leave you with this food for thought. If there are doubts before your midsem, please ask me based on today. Okay, so we will continue this post midsem. So this I don't want to cover this right now. We'll cover how this leads to a very strong, the best, good convergence rate. Okay. So is there any question, doubt you have based on today's discussion? Anything for midsem?
What is the last topic for midsem?
So last topic is where we have just left off. I'm deliberately not doing the smooth plus strong convex. This is I'm going to leave it at this, right? I have 5 to 7 minutes, so I'm going to continue if you have no questions. So midsem is until this point, but I want to just continue, make use of my remaining time to see simple completion of this proof. I will not ask that in the midsem though. Okay. That fine? So for midsem, I've just given you a hint of how strong convexity might change things, right? Change the scenario. But the exact convergence proof, I want to do it in the remaining 10 minutes. I will not be covering it in the midsem. Okay. Any questions so far? If there are no questions, I'd like to just continue this discussion. A smooth plus strongly convex function. And the substitutions are very simple. I mean, there's really no rocket science left, right? So what we have done is the straightforward 3D algebra. Whatever I highlighted in the previous slide, I've now I tried to put it as a thought process for you. This is post midsem, as I said. So I'm just going to use this manifestation of trick one. Okay, trick one here, and see what's the next trick to bring up. So what's the next trick to bring up? Yeah, students can actually stay back and think, right? So this is all kind of intellectual stimulation. You do telescopic summing from here. Well, no, if you do telescopic summing, you only use convexity, right? I mean, or use convexity and then telescopic summing. What we could do here is strong convexity and then look at telescopic summing. So instead, the deviation would be, instead of convexity followed by telescopic summing, why not strong convexity next? Okay, so what happens if you use strong convexity? I gave a hint in the previous slide. So we'll have a stronger lower bound. So if this dot product is lower bounded by f of xt minus f of x star plus this additional term. The additional term is only because of strong convexity. Okay. What can we do next? Well, we can put these two together, right? We can combine 10 and 11. Putting 10 and 11 together. Again, it's going to be rearrangement of terms. So f of xt minus f of x star, you bring to the left hand side. And that's what we have done here. Oh, sorry. I have not brought it to the left hand side. I've just flipped the inequality. Yeah, so I have flipped the inequality here. And the other part is substitute, right? Substitute for gt x t minus x star. So this has been substituted. Here. The brown terms, even though they are separated now, what I've done is brought the one part of the brown term to the left hand side. So along with gt transpose xt minus x star. So that's what you see here. Okay. Now xt plus 1 minus x star, which is sitting out here, I'm trying to isolate it from the other terms. For obvious reasons, we are going to get into some telescopic summing, but there's also another reason. You'll find that this is probably where things start getting slightly trickier. Okay, because I have this term xt. Just note this term. Okay, xt minus x star. Now this xt minus x star also figures here. So therefore, telescopic summing cannot be applied directly. I need to do a little bit more because these terms don't get cancelled out, right? So, but that's also one reason why we get faster rate of convergence. Note that a simple use of telescopic summing not work, since the terms from t and t plus 1 would get cancelled. Okay, so this might look like, oh, bad thing, convergence becoming complicated. Yeah, there's a little bit more complexity, but it's also good because this is what leads to better rate of convergence. The things are actually shrinking. What you get now by combining is you get this 1 minus mu, there's 1 from here and minus mu gamma. Okay, gamma is coming also because there's a gamma square here. We'll deal with this a little bit more carefully post midsem, but I wanted to give you a hint why things get complex. It's not that telescopic summing works immediately. Okay, so rest we'll do after midsems. And as I said, this additional part from slide number this whatever 23 onwards is not going to be part of midsem, largely because we have not even completed the proof. I've just tried to tickle your imagination on how we would proceed given that straightforward telescopic summing doesn't work. Okay. Again, any other final question, or we are going to conclude for today?
Sir, I had a question pertaining to the exam.
Right, please go ahead.
So there was a form circulated at the beginning of end of last month about those who are in campus.
Right.
At that time, I was not in campus, so I put I was not in campus. But now I am back in campus. So I'll go to the exam hall, but my question is whether I am listed as one as one of the.
Yeah. Anyone who's on the campus is listed, not a problem. So the listing is not a big deal.
Okay, sir. Thank you, sir.
Yeah.
That's all.
Please be there. You're supposed to
Yes,
attempt
absolutely.
it personally. Thanks for bringing that up,
Thank you, sir.
Shivayan.
Uh,
Sir, in the mock test of Code Tantra, we had an option of uploading the scanned answer sheet written. For that, we need an additional mobile device. So will it be like that in midsem also? We'll have to carry an additional mobile for scanning?
A good question. Can you just post that on the Teams? I'll get it routed through the Code Tantra team.
Yes, sir, I've already posted.
You posted, right? I'll get it answered. Thanks.
Sir, so there will be like a long answer writing, which we'll have to write.
Yes. I'll also be giving you sheets. We'll be giving you sheets. If you have your own notebook, that's also fine. But everything has to be uploaded. So what we will correct is what you have uploaded. No physical answers will be passed on. Is that okay?
Yes.
Any other question? Okay, if there are none, we'll close for today. Thanks to everyone. Wish you all the best. We'll meet on Tuesday evening, I guess, right? Tuesday evening, 6 p.m. Thanks. The venue, I'll let you know as soon as I hear from the institute.